Environmental sustainability is a topic that we hear about frequently and is extremely important in the modern world. We lose millions of acres of forest every year from fires, urban expansion, and overharvesting. However, reforestation is difficult. Reforestation requires people to carry water to remote areas and give up valuable drinking water. There is currently no way that people can plant a tree and then walk away and let it grow. New plants require constant attention from the native people of the region being reforested. However, trees and undergrowth are important and cannot just be forgotten. We endeavor to find a way to get water to new plants without physical labor or giving up copious amounts of drinking water.
Our problem statement is that getting water to arid regions and difficult terrain is a challenge for reforestation, as the cost of transporting water is high due to the fact that plants require substantial amounts of water to establish themselves.
Some solutions to this problem capture rainwater near the plant, but they do not account for the soil moisture. This means that it will still release water to the plant when the soil is moist, which can potentially waste water and even overwater the plant, which could kill the plant eventually. Moreover, many of the slow-release products are not recharged with rainwater. They're only rechargeable by hose. So, in reality, our system is more efficient. Our design requirements require our prototype to provide enough water to keep the soil at a constant saturation level. The equipment will be made out of materials that can be obtained in areas with little infrastructure and resources. The equipment should not damage the environment during or after its use. It must require a minimal amount of maintenance to last at least 6 months without repair. And looking at our decision matrix, it looks like Ryan's fourth design was 5s all across the board with viability, size, weight, and cost. So that is the prototype we went with overall. Some of our constraints for our design was that the cost of the small-scale system should not exceed $400. The battery, inverter, pump, Arduino system, and the solar panel all costed somewhere around $350. The equipment needed is somewhat expensive, but for a country, the price tag is relatively cheap at a large scale. And obviously, the prototype must be completed by May 1st.
Our device consists of several main parts. First, we have a solar panel that is connected to a large battery. From there, an inverter is connected to the battery to provide AC current to both the Arduino and the pump. The pump and the Arduino are supplied with power, and hoses are connected to both the input and output of the pump to allow the pump to move water to a distant location. For the actual testing, the soil saturation sensor is placed in the soil at a reasonable depth, 1 to 2 feet depending on the plant. We want the soil saturation sensor to be at the same elevation that the roots of that plant are. The device was observed to determine if the device would activate and pump sufficient amounts of water to saturate the soil enough to deactivate the device. A second test will be an observation on whether or not the sensor and the system will work consistently. There are 2 main tests for our project, the actual test and a hypothetical test. We've already discussed the actual test, which is just the functioning of our project. For our hypothetical test, we took soil data and rainfall data around Reno to determine if we could place our device in a certain area and have it be efficient in growing shrubs or saplings. We selected a small valley where the Collin Ranch fire had burned through in the past couple years, right off of South McCarran. We gathered data about the amount of runoff and the permeability of the soil in the area. We compiled data to determine whether or not our device would be suitable for that area. The 2 tests that we described here will provide us with a basis for understanding whether or not our device will be effective in reforesting areas. Within our project, we implemented all 4 of the different STEM principles. For science, we used physics and environmental science. We calculated soil data, runoff statistics, and soil composition to calculate our device's efficiency and necessary components for success in arid soil. We also utilized physics principles when putting together our device so that it would work efficiently. For technology, we used solar panels, batteries, an inverter, an Arduino, and a water pump. Electrical engineering was the basis of this project. Wires were soldered and connected to the power source, pump, Arduino, and inverter. Math was used to calculate the average water runoff in certain areas and how much power was needed to supply the device. Through calculations, it was determined what kind of pump would be necessary, head pressure, and overall efficiency of our project.
Our prototype met our design specifications. It was made with materials and equipment that wasn't extraordinarily expensive or too difficult to obtain for third world countries. In the future, we would like to place our project in an enclosure to minimize the risk of water or elemental damage. Another improvement we could have made was implementing multiple sensors and low-cost valves to increase the efficiency and accuracy of our prototype by allowing individual areas to be irrigated separately.